Welcome everybody. Welcome to this webinar on OpenWindPower. My name is Parvinder Jhita, and I'd like to discuss the agenda first. The first presentation will be on fixed foundation capabilities, and then Dr. Daniel Wien will discuss the floating foundation capabilities, and Dr. Wien will then discuss the capabilities of our Moses product. This will be followed by Bitna So, who will discuss the structural interoperability of OpenWindPower. I'd like to start with the fixed foundation capabilities. SACS. In SACS, we have full life cycle applications for the analysis and design of fixed wind turbine platforms, all the way from fabrication to installation, to in-place conditions, and finally decommissioning. For fabrication, the jacket is manufactured in portions which are then rolled over using slings and joined together. This process is called bent roll-up. In this case, the structure is designed to resist sling forces, and we have various products within SACS which can handle this scenario. For the transportation analysis, the jacket structure is designed to resist the gravity load and inertial loads resulting from the vessel motion. The sea fasteners, however, are designed to resist the inertial loads. We have two products called tow and sea state, which can be used to generate these inertial loads. For the installation lift analysis, the jacket is designed to resist lift forces and buoyancy loads as it's lowered into the water. We have interfaces to general purpose finite element meshing packages such as FEMAP and FEMGV, which can be used to do a detailed finite element analysis of the lift pad eyes. For the in-place condition, the structure is analyzed and designed to resist both the maximum operational and storm wave loads, including wind and current loading from different directions. The foundation is described by nonlinear soil behavior, and we have various options to do that. We have the API PYTZ adhesion soil option and the user-defined PYTZ and adhesion soil input. The SACS fatigue module can conduct both spectral, time history, and deterministic fatigue. For the spectral fatigue, we have the various spectra, including the Pearson-Moskowitz, Ochi-Hubble, John Swap, and a user-defined spectra as well. The SN capabilities are already programmed in using API, HSE, AWS, NORSOC, ISO, and user-defined SN curves. The SCF options include FMU, Quang & Wordsworth, Smedley & Fisher, Marshall, and DNV. The member code check options include API, AISC, the Canadian Code Check, British Standards, ISO, Eurocodes, and the NORSOC standard. And similarly for the joint design, we have API, ISO, NORSOC standards, and the Norwegian Petroleum Directorate standards. Now, depending on where the structure is located, it may also require a dynamic earthquake analysis, and a dynamic response package here can conduct both spectral and time history earthquake analysis. For the spectral, the API response spectra is built in. The user can also define his own spectra, and the modes can be combined either through an SRSS or a CQC approach. And we also generate equivalent static loads to make sure the foundation can also survive the earthquake loading. For the time history, we allow variable time step integration We allow for a nonlinear fluid damping, and of course linear, quadratic, or cubic interpolation between time history input values. The nonlinear ship impact analysis can be conducted using the SACS collapse module, which can account for both geometric and material nonlinearities resulting from a ship impact event. We can automatically mesh the impact points to account for local indentation effects, and both quasi-static and dynamic impact analysis are possible in SACS. For nonlinear ship impact analysis, we designed for both low energy and high energy impacts. The low energy is also referred to as an operational impact, where the jacket bracing is designed to survive operational impact. Partial load yielding at the impact point is allowed. For the high energy or accidental impact, the jacket legs are designed to survive the accidental impact. The face and leg joints are also designed to survive the accidental loading. However, the jacket bracing is allowed to fail, but the structure has to survive the loss of that brace member. We can automatically generate a 3D mesh for a tubular member to account for a ship impact analysis, and the mesh is seamlessly integrated back into the SACS beam model. The user has full control of the mesh density here. And just to show you how easy this is, this animation will show how to mesh a jacket member. We can zoom in onto the point of interest and basically provide the group labels for the plates that are going to be generated and the number of joints around the circumference of the tubular. Also have the option to do quadrilateral or triangular plate meshing. So once you've done this, then you can go ahead and do a ship impact analysis on the leg. Also for a joint impact, again, we can mesh the joint automatically, and this is done in seconds. We automatically identify the cord and the brace members, and again, the joint mesh is then seamlessly integrated back into the SACS beam model, and again, the user has full control of the mesh density. This animation shows how easy it is to mesh a joint. Let's zoom in to a joint that we want to mesh, and then we'll take the rendering off so we can select the joint, and then we go to the mesh joint option, where we define the joint name, select the joint name. We can identify the intersection subdivisions for the brace, and then also the length of members to be meshed. This will generate an input file, a list file, which defines the plates and the nodes that have been generated. Again, the mesh is seamlessly integrated back into the beam model. We can zoom in to look at the mesh, turn off the joints, put the rendering back on to show you how it's connected back into the beam model. Again, you have full control of the mesh density. You zoom in, you'll see you've got a very fine mesh in this area, and of course a mesh further away. So once you have done this, you can do a ship impact analysis on the joint itself. This animation here looks at a typical impact analysis on a leg member. This diagram here represents the modes that are accounted for in the response of the structure, and in this case, this is the ship, and it hits the jacket structure, and you have the response of the structure, and then finally the ship is pushed away. Next, I'd like to discuss the fixed foundation applications we have. It's a typical wind turbine structure here. We have three sources of loading. We have the wind load on the turbine, wind load on the structure, and the wave load on the structure. The dynamic response of the structure is coupled to all these three sources of loading. So we'll talk about coupled and uncoupled analysis later on. In this case, the wind loading on the jacket and the tower can be generated by a wind spectrum, where we have the one Kármán, API, Harris, and Camel spectrum. The API and the Camel spectrum are height dependent, where the one Kármán and Harris are not. We can also generate the loads directly by inputting a wind velocity time history. For the wave loads can be represented either via wave spectrum or a time history of the surface profile. And again, we have the various spectrum available, which includes Pearson-Moiscovich, John Swap, Ochi-Hubble, and the user can also define his own spectrum. The wind load on the turbine causes the rotation of the wind turbine, which in turn generates mechanical and aerodynamic forces on the base of the tower. And these can be represented by a force time history input. So provided we have the three forces, turbine mechanical, aerodynamic time history, or wind spectrum, wind velocity time history, or wave spectrum, or wave surface profile time history, we can conduct a full fatigue and strength analysis of the structure. Now, SACS, we have various ways of analyzing the structure. We have our own wind turbine uncoupled process. We also have an interface to NREL's FAST program. It's an aeroelastic program, and also an interface to DNV's GH bladed product. We can also connect to Siemens B-Hawk and MHI Vestas using the Craig-Bampton dynamic super element capabilities. We can also read the direct time history input from B-Hawk and Flex 5, so the user does not have to change formats. I'd like to next go on to the uncoupled wind process. It's uncoupled in this case because the turbine loads are provided by a third party, whereas the wave and wind loads are generated by the SACS program. Here we can start off by providing a model to GH bladed by modeling it in SACS, and again we analyze the wave, wind loads, and the turbine loads using SACS, and then finally post-process, in other words, fatigue and member check, joint design in SACS. This is an iterative process because in this case the response of the structure in the third-party program has to match the response of the structure in SACS. It can take up to about 3 iterations to get to a result. To do an uncoupled analysis, it's fairly straightforward. We have a control file which defines the locations of the directories for the various simulations, and we also provide a partial fatigue input file which does not contain the fatigue load cases. These are automatically generated by the uncoupled process. We can run the analysis through a multi-core process, and then finally this will yield our fatigue results. For strength analysis, the process is a little bit more cumbersome in that if we have 15,000 simulations, each 600 seconds long, and the analysis increment of 0.05 seconds, this will generate 180 million load cases and therefore 180 million unity checks. To overcome this process, what we do is we provide a controlled SACS input file, partial C-state input file, and PSI input file, and a joint CAN input file. Again, we run a multi-core analysis, and all the results are then stored in a SQL-like database. We then scan this database for our critical unity checks, and those will be our strength results, basically. This animation shows how easy it is to do one of these analyses. We have 4 simulations here. We first go to the utilities and choose the SACS wind turbine process. Next, we provided a control file, and we set the upper bounds for the unity checks for members and joints. And then we simply hit run, and this is now running in parallel and now doing the post-processing. And then the process generates a joint can summary report and a member summary report. Look at the joint can one. Here we have our maximum unity checks here. These are all above the upper limit that's provided by the user, and these are the member per unity checks. It's very straightforward. Now, to analyze wind turbine structure requires the use of analysis of thousands and thousands of simulations. Typically, maybe around 10,000 simulations for a fatigue analysis and 15,000 simulations for strength analysis. This requires a lot of input from the user. So to overcome this, we have a product called the Wind Turbine Job Creator. This uses an Excel spreadsheet to generate input files and the directory structure for the many design load cases, the thousands of load cases, and it generates them in the format required for Bentley's analytical cloud services. The Excel spreadsheet is also used to update parameters in the input files of a base set of files provided by the user to create input files for all time history load cases. Now, of course, this can generate, if you were to do this manually, it would take you a month of Sundays. Here, we can generate the 15,000 load cases in a matter of minutes. Next, I'd like to discuss our interface to NREL's fast aeroelastic program. In this case, what we can do is we can generate the jacket model in SACS and the turbine tower and the turbine itself in fast. And then we will do a fully coupled analysis using fast and SACS, and then finally post-processing, i.e. member checks, fatigue, and joint design in SACS. The process is, in this case, is what we do is initially we take the jacket model and we reduce it to a super element and connect it to the bottom of the tower. Then we do a fully coupled solution. Again, next I'd like to discuss the SACS GH bladed interface. Here again, we can generate a model for GH bladed from SACS pre-seed, and then the full analysis is conducted. It's the full time history analysis conducted in GH bladed, and then we can use SACS for post-processing for fatigue, member checks, and joint design. For the GH bladed interface, SACS.control file is generated by the GH bladed program. And this basically contains a location of each simulation directory and also the probability of occurrence. Again, the analysis process is very simple, similar to the uncoupled. For a fatigue analysis, we supply a control file, a partial fatigue input file, and a GH bladed results file, or all the result files, or directories, I should say. Then we conduct a multi-core analysis, and then we generate the fatigue results. Again, for strength analysis, the process again is very similar to the uncoupled process, in that we have a control file, we have a post input file, a joint cat input file, and we have the GH bladed results. Again, we conduct a multi-core analysis. We store all the unity checks for the members and the joints in a SQLite database, and then we filter that database to give you the critical unity checks. We have also, modified this process to account for multiple safety factors. The GH-bladed product itself only considers a single safety factor for both the gravity and dynamic loads, whereas the IEC codes and the ISO codes require you to have a separate safety factor for the gravity load and a separate safety factor for the dynamic load. Here we begin with step one is we use our combined module to separate the dynamic and the gravitational dead load components. And then afterwards we apply our safety factor and recombine the dynamic and gravitational load cases using separate safety factors. And again, then we analyze the post-process the GH-bladed results in SACS. Next, I'd like to discuss the SACS dynamic superelement capabilities. This dynamic superelement capabilities allows us to connect to Siemens B-Hawk, the MHI Vestas Flex 5 product, and the GH-bladed aeroelastic product, and including also the FAST product. This slide shows a typical workflow using this dynamic superelement. We start with the SACS model. We conduct a modal and wave response analysis, and then after that we use our dynamic superelement module to generate the dynamic superelement. This is then in turn passed on to the turbine manufacturer, who conducts an aeroelastic analysis with the dynamic superelement, and then the force time history at the bottom of the tower is then passed to SACS, and we use the SACS uncoupled process to do the analysis, and finally we do the code checks in SACS as well. Oh, and the fatigue analysis also. To generate dynamic superelement, it's a three-step process. So we start with a modal analysis, which generates a mass file, mode file, and the dynamic superelement data file, the dynamic superelement transformation file. Now, if the user also wants to generate a load vector, then we would run the wave response module using the mass file, mode file, and the transformation file. This will generate the dynamic superelement force file. The last step here is to actually run the dynamic superelement using the dynamic superelement input file, the dynamic superelement data file, and the dynamic superelement force file. And this will generate our reduced stiffness matrix, a reduced mass matrix, damping matrix, and the reduced load vectors. And this can be passed on to the turbine manufacturer for him to connect to the bottom of the tower. And it's essentially a coupled analysis at the end of the day. Next, I'd like to discuss our parallel processing capabilities. Now, why would we need to have parallel processing? Well, since we have thousands and thousands of simulations, if you run the analysis in parallel, this allows the analysis times to be reduced, and therefore allows the structural engineer more time to optimize the structure. Now, Bentley's cloud computing, the benefits here are the cloud has thousands of nodes available for parallel processing, so it can conduct analysis really, really quickly. The drawback is it's a slow upload of large files, so the results files from GH-bladed are not really recommended for cloud computing. It's suitable for SACS uncoupled analysis because the upload is small files. We've done a benchmark here. We ran one simulation with 12,000 load cases using a single node, and the runtime took 1 hour and 15 minutes. Then we ran 1,000 simulations using 1,000 nodes, each with 12,000 load cases, and the runtime was 2 hours and 30 minutes. So it can drastically reduce your runtime. We also provide parallel processing capabilities using a computer network in your organization. So if you have 50 computers in your organization, we can access those and run in parallel using all those computers. This is really useful for the SACS GH-bladed interface because It has large results files, so we're not restricted here by the file size. Again, we did some benchmarks here, and it turns out the solid-state drives actually give you better performance. Next, I'd like to discuss our monopile foundation design capabilities. And here, first we will look at the loads on large tubular columns. Essentially what we do here is we use the McCamey and Fuchs approach. And these guys, what they did was they calibrated wave diffraction module and adjusted the coefficient of mass to give you the same results as the diffraction model. And so this is applied for both in C state for static and wave response for a dynamic analysis. This slide shows here the change in base shear versus the diameter of the monopile, and we pass a wave through that. And as you can see, when the diameter is small, both McCamey and Fuchs and Morrison's equation give you the same answer. As the diameter increases, then we get a divergence in results. We also have a product, a Plexus product called Modato, which was, which was developed after the PISA project. Essentially, basically what the PISA project, this is a project conducted at Oxford University in London. It shows that the traditional API methods of getting the pile capacity drastically underestimate the capacity of the large diameter piles. So we have both here an FE and 1D parametric model here. We have an interface to Modato where we can generate the end moment resistance and the end shear resistance curves from Modato and use them in our Pile 3D program. And also we can get the end theta curves from Modato as well. And again, this is validated against Plexus. Another capability we have for monopiles is the ability to generate radial damping. This is based upon master's thesis by Michael Ferris Cook, and basically it accounts for structural damping, wave radiation damping, viscous hydrodynamic damping, and soil damping as well. We can now also generate fatigue results at various points on the circumference of a cylinder. In the past, we used to give you just one value, which was the maximum value, but now we provide the values at different locations. To ensure that the structure sees the Hmax wave, we can blend an Hmax wave using the stream function wave back into the random C state. And we also have the capability to modify the coefficient of drag to account for the peak slap load. Next, I'd like to discuss the tidal energy capabilities. Our interface to GH bladed also gives us our interface to tidal bladed as well. Again, we can start with the SACS model, export that into tidal bladed, do a full analysis in tidal bladed, and bring the results back into SACS for code checking. Modify the model if needed and repeat the process. This video shows here the actual animation of tidal turbine. And basically, these are located in areas where you have high tidal flows, such as an estuary or Now, I'd like to talk next about the various clients we have. We have clients such as COE, Keystone, Goldwind, the China Classification Society, Lloyd's Register, Durantia, and Van Hattem and Blankenboot, which these guys design monopiles. And basically, we have a lot of clients out there using the product. Our development partners include Garad Hussain, with which we developed the SACS G8-related interface for post-processing. We worked with Lloyd's Renewable Division for the SACS uncoupled process, and we worked with Siemens to create our dynamic super element, Craig Bampton dynamic super element capabilities. And we worked with Keystone to develop our parallel processing and the grid network, and NREL to develop our SACS fast interface. Next, I'd like to discuss some OpenWind projects in Europe. And these include the London Array Wind Farm. This is comprised of 175 foundations. It's one of the largest wind farms in the world. And here we have 175 monopile foundations, water depth of up to 25 meters. Diameters of the monopile varies from 4.7 to 5.7 diameters. And we have 40 meters penetration below the mudline. These are our COE slides. And of course, they say the structure is modeled with beam elements, and the soil is modeled with PY curves, and the calculations are carried out using SACS. SACS was also used, or the OpenWindPower fixed foundation was also used in the Wickinger wind farm in Germany, developed, or structures were designed by COE. Here we have 70 platforms with a water depth ranging from 37 meters to 43 meters. In the USA, the OpenWindPower product was used to design the first offshore wind farm in the US waters. And this is the Block Island wind farm. It's 551 meter tall foundations. The water depth is around 28 meters, and it is comprised of 6 megawatt Alstom turbines. Next, projects in China. I would say we have basically the SACS wind turbine, or the SACS, the OpenWindPower has been used to design, I'd say, 90% of all offshore wind farms in China. The first wind farm in China, one furthest from the shore, first substation, the largest wind farm in China, the first 110 megawatt substation, and one that won the national award there, and the first conceptual wind farm in intertidal areas also. Well, that brings me to the end of my presentation, and I'd like to hand you over now to Dr. Daniel Wien to discuss the OpenWindPower floating foundation capabilities. Thank you.